Hello, my name is Tarik Tosun, and I'm presenting a paper entitled Perception-Informed Autonomous Environment Augmentation with Modular Robots. So what do we mean by environment augmentation? Basically, we're talking about robots changing their environments by building structures that make a task easier. This is a familiar human experience. If we need to reach an object on a high shelf, we'll place a step stool next to the shelf, changing our environment in a way that makes it work for us. There's been a lot of excellent existing work on robotic construction. However, in almost all of this work, the goal of construction is the structure itself. In this paper, we use construction to complete extrinsic tasks, for example, building a bridge across a gap to reach a goal region. In this project, we use the S'mores EP modular robot, which consists of a number of robot modules which can be connected in many different ways to form bodies with different capabilities. We introduced the new block and wedge modules shown below. Using these building blocks, S'mores EP can build ramps and bridges that let it surmount large obstacles. We expand on an existing system for high-level autonomy with modular robots. Tasks are specified at a high level, and the system automatically selects appropriate configurations and behaviors to satisfy the task objectives. In this work, we allow the high-level planner to alter the properties of the environment by building structures whenever it provides a benefit to the robot. For example, in this scenario, the robot's task is to open the bottom drawer, climb on top of it, open the second drawer, and take a picture of what's inside. To determine whether it can climb into the bottom drawer, the robot moves to an appropriate vantage point to inspect the drawer with its RGBD camera. Based on environment characterization, the high-level planner recognizes that this ledge is too high for any configuration in its design library to climb. However, it also identifies a pre-built ramp structure near the drawer. Recognizing that the ramp structure can be used to overcome the ledge obstacle, the high-level planner commands the robot to retrieve the ramp. It backs up to take another look at the ledge, confirming an appropriate placement location for the ramp. It then places the ramp next to the drawer, augmenting this previously problematic environment to make it possible to complete its task. The front three modules break off and climb onto the books. Once on top, localization is provided by the downward-facing RGB camera on the sensor module. The modules orient themselves to face the second drawer, latch to it using their electropermanent magnets, and pull it open, allowing the sensor module to take a picture of the missing objects. In Experiment 2, the robot begins on the left table and is simply tasked with moving to the pink goal marker on the right table. The robot immediately recognizes that the goal marker is isolated from its own location by a 16-centimeter gap between the two tables. Recognizing that it would be unable to cross this gap on its own, the robot searches for materials to augment its environment. It identifies 3 available augmentation modules nearby and assembles them into a bridge. Once the bridge is assembled, the robot maneuvers to one of the bridge placement candidate points identified by its environment characterization algorithm. It places the bridge across the gap, then reconfigures, and crosses the bridge, completing its mission.